By now, you'll have had a lot of opportunity to practice differentiating common functions, and you'll have learnt many techniques of differentiation. So, for example, if I were to give you a function, let's call this function capital F of x. If it's a fairly simple function, you'll know how to differentiate it. And so, by differentiating it, you'll be able to calculate its derivative, which you'll remember we denote as df dx. So that's a process that you're very familiar with already. Now, in this unit, we're going to refer to df dx as little f of x. So, little f of x is the derivative of big F of x. Let me write that down. Little f of x is the derivative of big F of x. And as I say, that's a process that you're very familiar with. What we want to do now is try to work this process in reverse, work it backwards. In other words, we want to start with little f and try and come back this route and try and find the function or functions, capital F, which when they are differentiated will give you little f. So we want to carry out this process in reverse. We can think of this as anti-differentiation. So we can think of this anti-differentiation as differentiation in reverse. So big F of x we're going to call the antiderivative of little f of x. So bear these two results in mind and try not to get confused with the capital F and the lowercase f. Little f is the derivative of big F, because little f is df dx, and big F is the antiderivative of little f. Now, you may have already looked at a previous video called Integration as Summation. And in that video, the concept of an integral is defined in terms of the sum of lots of rectangular areas under a curve. To calculate an integral, you need to find the limit of a sum. And that's a very cumbersome and impractical process. What we're going to learn about in this video is how to find integrals, not by finding the limit of a sum, but instead by using antiderivatives. Let's start off with an example. Suppose we start off with the function capital F of x is equal to 3x squared plus 7x minus 2. And what I'm going to do is something that you're already very familiar with. We're going to differentiate it. And if we differentiate it, we'll get df dx equals, term by term, the derivative of 3x squared is going to be 2 3s are 6x, and the derivative of 7x is just going to be 7. What about the minus 2? Well, you'll remember that the derivative of a constant is 0, so when we do this differentiation process, the minus 2 disappears. So our derivative, df dx, is just 6x plus 7. So I'm going to write little f of x is 6x plus 7, and think about what will happen when we reverse the process, when we do anti-differentiation. Ask yourself, what is an antiderivative of 6x plus 7? Now, we already have an answer to this question. An antiderivative of 6x plus 7 is 3x squared plus 7x minus 2. So the answer is f of x is 3x squared plus 7x minus 2. But I'm afraid that's not the whole story. We've already seen that when we differentiated 3x squared plus 7x minus 2, the minus 2 disappeared. In other words, whatever number had been in here, whether that minus 2 had been minus 8 or plus 10 or 0, whatever, it would still have disappeared. We've lost some information during this process of differentiation. And when we want to reverse it, when we want to start with the 6x add 7 and work it backwards, we've really no idea what that minus 2 might have been. It could have been another number. So this leads us to the conclusion that once we've found an antiderivative, like this one, 3x squared plus 7x minus 2, then any constant added onto this will still be an antiderivative. If f of x is an antiderivative of little f of x, then so too is f of x, the antiderivative we've found, plus any constant at all we choose. C is what we call an arbitrary constant. Any value of c, any constant, we can add on to the antiderivative we've found, and then we've got another antiderivative. So in fact, there are lots and lots of antiderivatives of 6x plus 7. Just as another example, we could have had over here 3x squared plus 7x minus 8, or even just 3x squared plus 7x, where the constant term was 0. So lots and lots of different antiderivatives for a single term over here. Let's do another example. Suppose this time we look at a cubic function. Let's suppose f of x is 4x cubed minus 7x squared plus 12x minus 4. Again, you know how to differentiate this. You've had a lot of practice differentiating functions like this. So the derivative, df dx, is going to be 3 fours are 12x squared. The derivative of minus 7x squared is going to be minus 14x. And the derivative of 12x is just 12. So think of our little f of x as being the function 12x squared minus 14x add 12. Notice again the point that the minus 4 in the differentiation process disappears. So now ask the question, what's an antiderivative of this function here, little f? Well, we've got one answer. It's on the page already. It's this. Big F is an antiderivative of little f. But we've seen that any constant added on here will still yield another antiderivative. So we can write down lots of other ones. For example, if we add on a constant, and let's suppose we add on the constant 10 onto this one, then we'll get the function 4x cubed minus 7x squared plus 12x plus 6 is also an antiderivative of little f. And the same goes by adding on any other constant at all we choose. If we add on minus 6 to this, we'll get 4x cubed minus 7x squared plus 12x, and adding on minus 6 will just leave us this. So that is another antiderivative. There's an infinite number of antiderivatives of little f. Now, in all the examples we've looked at, I've, in a sense, given you the answer right at the beginning because we started with big F, we differentiated it to find little f, so we knew the answer all the time. In practice, you won't know the answer all the time. So one way that we can help ourselves is by referring to a table of antiderivatives. Now, a table of antiderivatives will look something like this one. There's a copy of this in the notes accompanying the video. And a table of antiderivatives will list lots of functions little f, and then their antiderivative, big F, in the next column. And you'll see every antiderivative will have a plus c attached to it, where c is an arbitrary constant, any constant you choose. What I want to do now is I want to link the concept of an antiderivative with integration as summation. Let's think of a function y equals f of x. And let's suppose the graph of the function looks like this. I'm going to consider functions which lie entirely above the x-axis. So I'm going to restrict our attention to the region above the x-axis. We're looking up here. And also I want to restrict attention to the right of the y-axis. So I'm looking to the right of this line here. Let's ask ourselves, what is the area under the graph of y equals f of x? Well, surely that depends upon how far I want to move to the right-hand side. Let's suppose I want to move to the place where x has an x-coordinate x. Then clearly, if x is a large number, the area under this graph here will be large, whereas if x is a small number, the area under the graph will be quite small. Indeed, if x is actually 0, so this line is actually lying on the y-axis, then the area under the graph will be 0. I'm going to denote the area under the graph by A. So A is the area under y is f of x. And as I've just said, the area will depend upon the value that we choose for x. In other words, A is a function of x. A depends upon x. So we write that like this. A is A of x. And that shows the dependence of the area on the value we choose for x. As I said, large x, larger area, small x, smaller area. Ask yourself, what is the height of this line here? Well, this point here lies on the curve y equals f of x. So the y value at that point is simply the function evaluated at this x value. So the y value here is just f of x. In other words, the height of this line, or the length of this line, is just f of x, the function evaluated at this point. Now I'd like you to think what happens if we just increase x by a very small amount. So I want to just move this point a little bit further to the right and see what happens. I'm going to increase x by a little bit, and that little bit, that distance in here, I'm going to call delta x. Delta x stands for a small change in x, or we call it a small increment in x. By increasing x a little bit, what we're doing is we're adding a little bit more to this area. This is the additional contribution to the area, this shaded region in here. And that's a little bit extra area, so I'm going to call that delta A. That's an increment in area, a change in area. I'm going to write down an expression for delta A. Try and work it out. Let's try and see what it is. Well, I can't get it exactly, but if I note that the height of this line is f of x, and the width of this column in here is delta x, then I can get an approximate value for this area by assuming that it's a rectangular section. In other words, I'm going to ignore this little bit at the top in there. If I assume it's a rectangular section, then the area here, this additional area, delta A, is f of x multiplied by delta x. Now that's only approximately true, so this is really an approximately equal to symbol. This additional area is approximately equal to f of x times delta x. Let me now divide both sides by delta x. That's going to give me delta A over delta x is approximately equal to f of x. How can we make it more accurate? Well, one way we can make this more accurate is by choosing this column to be even thinner, by letting delta x be smaller, because then this additional contribution that I've got in here that I didn't count is reducing in size. So what I want to do is I want to let delta x get even smaller and smaller. And in the end, I want to take the limit as delta x tends to 0 of delta a over delta x. And when I do that, this approximation in here will become exact, and that will give us f of x. Now, if you've studied the unit on differentiation from first principles, you'll realize that this in here is the definition of the derivative of a with respect to x, which we write as dA dx. So we have the result that dA dx is a little f of x. Let's explore this a little bit further. We have that dA dx is a little f of x. What does this mean? Well, it means that little f is the derivative of a but it also means, if we think back to the discussion that we had at the beginning of this video, that a must be the antiderivative of f. A is an antiderivative of f. In other words, the area is f of x, the antiderivative of little f, plus any constant. That's going to be an important result. What it's saying is that if we have a function, y is f of x, and we want to find the area under the graph, what we do is we calculate an antiderivative of little f, which is big F, and use this expression to find the area. There's one thing we don't know in this expression at the moment, and it's this c. C, remember, is an arbitrary constant. But we can get a value for c. If we just look back again to the graph I drew, and ask yourself, what will be the area under this curve when x is chosen to be 0? Well, if you remember, we said that if this vertical line here had been on the y-axis, then the area under the curve would have been 0. So this gives us a condition. It tells us that when x is 0, the area is 0. When x is 0, the area is 0. What does this mean? Well, the area being 0, x being 0, plus a constant. And this condition then gives us a value for c. So c must be equal to minus f of 0. And that value for c can go back in this result here. So we have the final result that the area under the graph is given by big F of x minus big F of 0. Let me just write that down again. Okay. Now let's look at this problem. Supposing that I'm interested in finding the area under the graph of y is little f of x up to the point where x has the value b. So I want the area from the y-axis, which is where we're working from, above the x-axis up to the point where x equals b. We can use this boxed formula here. When x is b, we'll get a of b, that's the area up to b, will be f of b minus f of 0. So this expression will give you the area up to b. suppose now I want the area up to A, and let's suppose A is about here. So now I'm interested in this area in here, which is the area from the y-axis up to A. Well, again, using the same formula, the area up to A, which is A of A, is f evaluated at the x value, which is A. Subtract big F of naught. So I have two expressions on the page here, one for the area up to B and one for the area up to A. Ask yourself, how do I find this area in here? That's the area between A and B. Well, the area between A and B we can think of as the area up to B subtract the area up to A. So if we find the difference of these two quantities, that will give us the area between A and B. So we get the area under y is f of x from x equals A to x equals B. It's the area under this graph from x is A to x is B is given by, well, it's the area up to B, subtract the area up to A. So if we just find the difference of these two quantities, we'll have f of B minus f of A and minus f of naught minus minus f of naught. These terms will cancel out. So in other words, that's the result we need. The area under this graph between A and B is just big F of B minus big F of A. Let me just write that down again. The area under y equals f of x between x is A and x is B is given by big F of B minus big F of A, where big F, remember, is an antiderivative of little f. Any antiderivative. So this is a very important result because it means that if I give you a function, little f of x, and you can calculate an antiderivative of it, big F, then you can find the area under the graph merely by evaluating that antiderivative at B, evaluating it at A, and finding the difference of the two quantities. Now, in the previous video on integration by summation, the area under a graph was found in a slightly different way. What was done there was that the area under the graph between A and B was found by dividing the area into lots of thin rectangular strips, finding the area of each of the rectangles and adding them all up. And doing that, we had this result, that the area under the graph between A and B was given by the limit, as delta x tends to 0, of the sum of all these rectangular areas, which was f of x delta x, between x is A and x is B. Now, if you're not familiar with that, I would advise you go back and have a look at that other video on integration by summation. But that formula for this area was derived in that video. And this formula defines what we mean by the definite integral from A to B of f of x dx. That's how we defined a definite integral. And if we wanted to define a definite integral, if we wanted to calculate a definite integral, in that video we had to do it through the process of finding the limit of a sum. Now, the process of finding the limit of a sum is quite cumbersome and impractical. But what we've learnt now is that we don't have to use the limit of a sum to find the area. We can use these antiderivatives because we've got two expressions for the area. We've got this expression as a definite integral, and we've got this expression in terms of antiderivatives. And if we pull all that together, we'll end up with this result, that the definite integral from a to b of f of x dx is f of b minus f of a. In other words, the definite integral of little f between the limits of a and b is found by evaluating this expression where big F is an antiderivative of little f. Let me write that formula down again. The integral from a to b of f of x dx is given by big F of b minus big F of a. Let me give you an example. Suppose we're interested in the problem of finding the area under the graph of y equals x squared. And let's suppose, for the sake of argument, we want the area under the graph between x is 0 and x is 1. So we're interested in this area. In the previous unit on integration as a summation, this was done by dividing this area into lots of thin rectangular strips and finding the area of each of those rectangles separately and then adding them all up. That gave rise to this formula, that the area is the limit as delta x tends to 0 of the sum from x equals 0 to x equals 1 of x squared delta x. So the area was expressed as the limit of a sum. And in turn, that defines the definite integral x is 0 to 1 of x squared dx. Now, up until now, if you wanted to work this area out, the way you would do it would be by finding the limit of this sum. But that's impractical and cumbersome. Instead, we're going to use this result using antiderivatives. Our little f of x, in this case, is x squared. And this formula at the top of the page tells us that we can evaluate this definite integral by finding an antiderivative, capital F. So we want to do that first. Well, if little f is x squared, big F of x, well, we want an antiderivative of x squared. And if you don't know what one is, you refer back to your table. An antiderivative of x squared is x cubed over 3 plus a constant. So in order to calculate this definite integral, what we need to do is evaluate the antiderivative capital F at b, that's the upper limit, which in this case is 1, and then at the lower limit, which in our case is 0. Let's work out f of 1. Well, f of 1 is going to be 1 cubed over 3, which is just a third, plus c. Let's work out big F of 0. Big F of 0 is going to be 0 cubed over 3, which is 0 plus c, so it's just c. And then we want to find the difference. F of 1 minus f of 0 will be a third plus c minus c. So the c's will cancel and we'll be just left with a third. In other words, to calculate this integral here, all we have to do is find the antiderivative capital F, evaluate it at the upper limit, evaluate it at the lower limit, find the difference, and the result is the third. That's the area under this graph between 0 and 1. Now let me just show you how we would normally set this out. We would normally set this out like this. We'd find an antiderivative of x squared, which we've seen is x cubed over 3 plus c. We don't normally write the plus c down. And the reason for that is when we're finding definite integrals, the c will always cancel out, as we saw here. The c's cancelled out in here, and that will always be the case, so we don't actually need to write a plus c down when we write down an antiderivative of x squared. It's conventional to write down the antiderivative in square brackets and to transfer the limits on the original integral, the 0 and 1, to the right-hand side over there, like so. What we then want to do is evaluate the antiderivative at the top limit. That corresponded to the f of b, or the f of 1. So we work this out at the top limit, which is 1 cubed over 3. We work it out at the bottom limit. That's the f of a, or the f of 0. We work this out at the lower limit, so we'll just get 0. And then we want the difference between the two, which is just going to give us a third. So that's the normal way we would set out a definite integral. So as we've seen, definite integration is very closely associated with antidifferentiation. Because of this, in general, it's useful to think of antidifferentiation as integration. And then we would often refer to a table like this one of antiderivatives as simply a table of integrals. And there'll be a table of integrals in the notes, and in later videos you'll be looking in much more detail at how to use a table of integrals. So think of the table of integrals as your table of antiderivatives, and vice versa. Very early on in the video, we looked at this problem. We started off with little f of x being equal to 4x cubed minus 7x squared plus 12x minus 4. We differentiated it to give 12x squared minus 14x plus 12. And then we said that an antiderivative of 12x squared minus 14x plus 12 was this function, capital F plus c. We've got a notation we can use now because we've linked antiderivatives to integrals. And the notation we would use is that the integral of 12x squared minus 14x plus 12 dx is equal to 4x cubed minus 7x squared plus 12x plus any arbitrary constant. And we call this an indefinite integral. And we say that the indefinite integral of 12x squared minus 14x plus 12 with respect to x is 4x cubed minus 7x squared plus 12x plus a constant of integration. Okay, in summary, what have we found? Well, we found that a definite integral, the integral from a to b of little f of x dx, we found that this is a number, and it's obtained from the formula f of b minus f of a, where big F is any antiderivative of little f. And we've also seen that the indefinite integral of f of x dx is a function, big F of x, plus an arbitrary constant, again where f is any antiderivative of little f, and c is an arbitrary constant. So in this video, we've learned how to do differentiation in reverse. We've learnt about antiderivatives, definite integrals, and indefinite integrals. In subsequent videos, you'll learn a lot more techniques of integration.